new balance?
Yes, please.
So, 1 N2, 3 H2, 2 NH3.
So 1, 3, 2. Can everyone do that? Good. That's important for the test that you can balance. So Le Chatelier's principle, we've been looking at reactants yields products, but a lot of reactions actually occur in equilibrium, meaning they can go both directions. And if a reaction is at equilibrium, it means the rate of the forward reaction is equal to the rate of the reverse reaction. So remember collision theory, these molecules need to collide with enough energy and in the proper orientation to become ammonia, right? To react and become ammonia. What type of reaction is this if it's going to the right? Synthesis reaction. And then if it was going to the left, decomposition reaction. So a lot of reactions occur in equilibrium. Now, Le Chatelier's principle says that if a stress is placed upon this at equilibrium, then it will adjust to minimize the equilibrium. Well, first of all, what does adjust mean? It means which way will these arrows dominate? Will it trend towards the products or will it trend towards the reactants? Will the equilibrium shift towards the products or will the equilibrium shift towards the reactants? So then you can think, what on earth stresses a system? Right? What is a stress to a chemical system? And the possible stresses to a chemical system are temperature, concentration, and what concentration means is just amounts. Concentration, temperature, pressure. Well, that's easy to remember when it has to do with stress. And this, I'm talking atmospheric pressure. Atmosphere. The weight of the atmosphere on the chemicals that are reactive. Now, you may not know this, but this nitrogen gas and hydrogen gas actually yield ammonia gas. So they are all the states of matter. You need nitrogen, hydrogen, but ammonia is also in the gaseous state. So do we understand equilibrium? So you would see the arrows going both directions if we're looking at a reaction in equilibrium. And remember, the rate is anything divided by time, right? So the forward, I say forward when it's going to the right, the forward rate of reaction is equal to the reverse rate of reaction when it's at equilibrium. So one's not overpowering the other. It's kind of like perfectly balanced, going back and forth. So Le Chatelier's principle is something you want to be able to predict what's going to happen when you apply any of these stresses. So the easiest one to think of is concentration. If you turn this chemical reaction into a ramekin of ketchup. Right? And we're just going to put this little equilibrium line down here. And it is full of ketchup. Nice, delicious ketchup. If you were to dip a French fry into this side of the ketchup, and the ketchup sticks to the French fry, and then you stick it in your mouth, right? What's going to happen to the equilibrium of the ketchup, or which way will the ketchup flow? Towards where you took it out. Does that make sense? I'm sorry?
Towards the area with less ketchup?
Towards the area with less ketchup. Yes, so if you were to remove a big blob of ketchup here and it went into your mouth, the ketchup would flow and fill in that amount. Well, that is equivalent to reducing the concentration, square brackets means concentration, reducing the concentration of NH3. Reducing the concentration of NH3 would cause the ketchup to flow to fill that in. Does that make sense? So reducing NH3 would cause an equilibrium shift to the right. I'm just going to draw the arrow. It would cause an equilibrium shift to the right. Does that make sense? Yeah? So what if you dipped your French fry in on this side and you pull some out? Which way will the ketchup flow? It would flow back in here. So reducing, let's say, what does this mean? Concentration of N2 shifts the equilibrium to the left. What about if I reduce H2? It also shifts to the left. Yeah? Now, over time, your ketchup's going to get lower. Over time, your ketchup's going to get lower, and if, like my kids, they give me the where's the ketchup? And then they get ketchup, squeeze, and they fill up the big pile of ketchup. You guys like ketchup? Yeah. So, if you added ketchup to this side, which way would the ketchup flow? Yeah, it's going to flow towards the reactants, right? Well, that is the same as increasing the concentration of NH3 will cause the shift towards the reactants. And the same thing on this side. Increasing either one of these or both, increasing either nitrogen or hydrogen or both, will shift the equilibrium towards the products. So increasing the concentration of N2 or the concentration of H2 will shift the equilibrium towards the products. Shift right, shift left, shift towards the products, shift towards the reactants. Right? That's what causes the shift. So that's how systems in equilibrium will respond to changes in concentration. So that's one of the stressors. Chatelia's principle: if you're at equilibrium and a stress is applied, the system will adjust to return to that equilibrium. So let's talk about temperature next. Reactions, as you may know, are classified as, you've probably heard this before a couple times, endothermic or exothermic, yes? And if we remember the energy diagrams for endothermic and exothermic, it's potential energy over time, We start with our reactants at some level of potential energy. We start with our reactants at some level of potential energy. So that's the nitrogen and hydrogen. They're at some level of potential energy. They have to overcome activation energy. Ooh. And now they're at a, now they're at the top. What's it? I think you probably learned it. Learn it. Did you learn activated complex with enzymes and substrates? The activated complex up there, activation energy, activated complex, transition state also. And then if it's endothermic, the products are at a higher energy. The products are at a higher energy than the reactants are. So if this was 50, this is 75. We have a positive change. Delta H is positive enthalpy change of plus 25. Right? If it's exothermic, the products end up at a lower potential energy than the reactants. The products end up at a lower. So this is 50 and 75 here. This is 25. So the delta, 25 minus 50, so the delta H is minus 25, and that would be an exothermic reaction. Now, just coming back to you guys, quick reminder. So if a chemical reaction is exothermic, we tend to see that. So our classic exothermic chemical reaction is our CH4 gas and oxygen gas. What's it going to yield? CO2 and H2O, and this is also a gas. And it also yielded, this is a combustion reaction, methane and oxygen, energy, right? You also get energy. Energy is released to the environment, right? So this is an exothermic reaction, right? Well, let's say at equilibrium, an exothermic reaction has heat on the product side, or energy on the product side, right? This energy we see as heat. So I'm just gonna write heat. Yeah, there's light and other stuff, but heat. So if it was at equilibrium, and here we are, we increase the temperature. We increase the temperature. That is the same as adding ketchup to this side, right? You literally treat the heat as another product. You just treat it as another product. So if the temperature of the surroundings is increased, that's a stress, right? And the equilibrium, if we add ketchup to this side, which way does the equilibrium shift? Yeah. So if you increase temperature of a exothermic or an exothermic reaction, increased temperature of an exothermic reaction, the equilibrium shifts towards reactants. So what if we lower the temperature of an exothermic reaction? That's the same as removing heat. Right? So if we lower the temperature of exothermic reaction, which way does the equilibrium shift? Anyone? Anyone know, or anyone have any idea? I lower the temperature. It's like dipping a French fry into this side of the ketchup and removing some. So it's going to shift towards the product, right? So if I lower the temperature of an exothermic reaction, the equilibrium shifts. I'm going to say right. You can say right now. Equilibrium shifts right. Now this is an exothermic reaction, which tells us that our heat is on the product side. Let's just do an endothermic reaction. So I'm going to have our heat plus A plus B yields C plus D in equilibrium, right? So this is endothermic. So what happens when you increase the temperature of an endothermic reaction? Which way will the equilibrium shift? It should shift right. So equilibrium shifts right. Because that's the same as adding ketchup to this side. Right? You increase the temperature. If I decrease the temperature, that's like taking ketchup out of that side, and the equilibrium will shift to fill that back in. Shifts left. Shifts left. Does this make sense to you guys?
Yeah.
Awesome. So we have handled concentration and temperature. You don't know what temperature is going to do unless you're given the information whether the reaction is endothermic or exothermic. If you're not given that information, you can't answer that question. You're not expected to know from here whether it's endothermic or exothermic. So what you'll see is a quantity of energy, like 25 joules, right? If you see a number of energy on either side, that's your heat. That's just your energy. So if you see it on the reactant side, that makes this endothermic. If you see it on the product side, it makes it exothermic. So the next pressure that a system in equilibrium, or the next stress that a system in equilibrium can have, is pressure. So think of, back to our ramekin of ketchup, we have 3 H2s. 1, 2, 3 H2s and 1 N2 on this side. And we have an NH3 and an NH3. And think of pushing down on it with a piston. If you were to push down on these particles, which way would they go to maintain as close as they can get to equilibrium? Well, when you increase pressure on the system, if anyone thought they're going to shift to the right, anyone thought that, you're dead on. There are more particles on this side than there are on this side. There are more moles on this side than there are on this side. So when you increase the pressure on a system, it will shift to the side of the fewer number of moles of gas. It will shift to the side of the fewer number of moles of gas. And then, so it's almost like squeezing out to keep it all at equilibrium. If you understand that part, then it is the opposite for decreasing pressure. Decreasing pressure is kind of like creating suction and giving them more room. If you're giving them more room, then it shifts towards more, they have more room, so it's going to shift to where they want more room. So it will shift to the left. Now, only counts with gas. Only counts with gas because they're the ones popping around left and right. So you picked up a worksheet. This table kind of sums it all up. Look down here. I don't know if it's so much a stress to a system at equilibrium, but adding a catalyst doesn't change the equilibrium. So adding a catalyst will not change a system at equilibrium. But what you're going to have to do on the test is very similar to these questions. For the reaction below, which change would cause this endothermic reaction in equilibrium to shift right? So we have a reaction. It told us it was endothermic. What does that tell you? Endothermic. Sorry?
It is on the left side.
Heat is on what?
The left side.
Heat is on the left side, yeah. There is a reactant of heat. All right, we got to put energy in. So read carefully. So which change would cause the equilibrium to shift to the right? We want to make more product, so what can we do? If we decrease the concentration of dihydrogen monosulfide, well, we need to know which one of these is dihydrogen monosulfide. Which one?
That's
That's methane. What's this one? What's that?
carbon sulfur.
No, carbon disulfide. Remember, if it's not a metal, you use prefixes. What's this one? Yeah, it's just hydrogen because it's a diatomic molecule. So dihydrogen monosulfide is here. If we decrease dihydrogen monosulfide, which way is it going to shift? It's going to shift to the left, right? Because we're pulling some out. What if we increase the pressure on the system? Which way does it shift if we increase the pressure? It's going to go to the fewest number of moles. So here there's 2 and 1, here there's 1 and 4. So should also shift this way. Does that make sense? Increase the temperature of the system. If I increase the temperature of an endothermic system, that's like adding ketchup to this side. Like I'm pouring ketchup into the bowl, so it will shift to the right. Increase the concentration of carbon disulfide. Everyone get that that's going to shift you that way? And decrease the concentration of methane. So that's me removing some ketchup from that side. So it will flow to go in there. So which would cause this reaction to shift to the right? There's only one of them. Let's see. When you're doing the multiple choice questions on the test, I recommend you do this because sometimes students just kind of read it wrong. Right? So if you mark which way it's going, one of them is going to stand out, and that's going to be your answer. So I'd like you to try to finish this worksheet up right now. But before you start that, before you start that, I need you to get out all of your Unit 6 worksheets. And if you are not sure what they are, you have this one, you have this one, you have this one, you have this one, this one, this one. Okay, so you have types of reactions. You have there's 10, 22, 23 predicting products. You have assigning oxidation numbers. You have balancing redox. You have voltaic cell. Yeah. Voltaic cell example. And now the shot. And FRQ test prep. Oh, and you have a table, a stamp table. So get these out, have them on your desk while you are working on the SHATS worksheet. Oh, you three of them to talk about. So these ions actually are leaving the zinc. These ions are being attached here. And this says cations, or positive ions. And then the sodium ions are actually, going this way. So the sulfurous sodium is going into here, these are going in there, and this is coming in here.
Yeah, and that's features that goes for not the other way. You can get right here. Yeah. So. Yeah, I think it's just register what like it's yeah, so like your side. I think everything. So what there's motion. I don't, yeah, yeah. My question is, I feel like
So it just means that energy is on the rise. Decreasing your volume is up. Smaller.
it goes to like normal capacity every increase the pressure. So the so we can maybe this is like 6, 7, and then this is 6, 8. So
Okay.
wait, isn't this right there? This is this right here is separated, and then that's 2, and this is 6. Yeah, sure.
You don't have to in all your
Let's just say. But that is Yeah, that's what I have, but I wasted. The volume looks like some Jesus. Hold it. Yes. I had this one. I know the way in the second. So it's. I don't know. Oh yeah, that makes sense. There's like the key on
We're trying to help.
but more for like this one.
Yeah, the volume, that's it. Or I should be.
Yeah.
The volume.
So like how do you know which like how do you know which one is size? Yeah.
So it's just one.
Oh,
Obviously that's the same. It's
1,
like
2, then there's 7.
yeah, so it was those size.
So like
it's basically big numbers.
okay. Number C.
Some of these things I'm like. I haven't done anything. I just like.
There's no change between that. It's just
More oxygen. Number 5 for C.
I don't know. Go that way.
Oh wait, 5 is C. Oh yeah, I don't know. Can we do that? Is that a thing?
Well, it's the same as everything even, and it just goes down. But this is gonna be carbon
Still
dioxide.
You're right. I don't know, that makes sense. We watch it makes sense. Hey, so it's a way for the heat. Yeah, but oh wait, do you have your contact? Yeah. Is there?
That's extra. We're adding more pressure.
Yeah.
You understand their design? Oh, you know, she might know she was adding more times.
Wait, why? Excuse me.
Doesn't it just move, you're increasing pressure, so it moves to the side of less mold. But they have the same, and they do no change. Next.
For 5 feet, so no change. But she said it was going to the left.
Let me go back over it.
Okay.
pause. All the ways it's going to shift. All the ways it's
Increase. Increase.
Try to catch up, guys. All the ways it's going to shift.
Do you want me to just for box or just everything?
Everything, all the way. You can get it. All the way.
Everywhere you get, it's just right. So.
Wait.
You chose to do
For a decrease. Wait, that's not kind of makes sense. I decrease the H2O concentration, and then it would increase the concentration of H2O. Oh. I can't add better was next to the concentration because it only force concentration to increase the amount of product. And I said increase. Hey Sarah, have you done 7 days? I got it.
Well, does it need to be obvious?
But you can Sarah. Yeah, I was
I'm not getting if there are balls on each side or equal. So what do you guys do?
okay.
Okay, so here's if I were to decrease the volume, it's like pushing right? So if you decrease the volume, decrease the increasing decreasing volume is synonymous with increasing pressure. Decreasing volume is the same thing as increasing pressure. So I wrote your test, and you have to predict products, assign oxidation numbers, identify the type of reaction. You don't have to balance the redox, but you have to identify. So this is the front page of that redox, right? You have to identify. The balancing redox was just a tool. So that is not on there. You do have to draw and label correctly a galvanic / voltaic cell, right? Because you got 3 of those. I'm not going to do the electrolytic. That's basically the Hoffman apparatus, which you've already done. But you do need to choose the right metals from a reduction table, right? So choose the correct metal and draw all of its parts. The shot worksheet you have right now is very similar to what you will have to do on the test. It is all FRQ. There are no multiple choice. You took those with the quizzes, kind of thing. So it's all FRQ, so that handout that I gave you, the FRQ test prep, would be ideal. You need to be able to assign oxidation numbers to get the formula rights after you predict the products. And once you have the formula rights, then you can balance it. So that is your Unit 6 test. You keep these worksheets because that's where I got the test from. Right? Keep the worksheets because that's where the test is from. Practice, practice, practice. So you get a nice A, nice simple A. Even put it in order. Yes, you may. Yes, you may take a picture of that. Next class is a review, so I need you to bring questions.
Hello. She got it. This is Miss Johnson. Would it be short?
Yep. Need the ketchup.
One person slaps. So the way I see.